Disadvantages of partitioning an SSD. A wise guy who goes by the name of Nick maintains a lengthy forum post on his views about building a powerful computer, directed towards playing Microsoft's Flight Simulator X, a very demanding piece of software. He sums up points about SSD drives somewhere, and he concludes the list as follows. Do not partition SSD. He doesn't elaborate on this unfortunately, but I wonder why he says this. What are the drawbacks of partitioning an SSD? Partitioning in this context meaning and GT semicolon equals 2 partitions.
SSDs do not, I repeat, do not work at the file system level. There is no one-to-one correlation between how the file system sees things and how the SSD sees things. Feel free to partition the SSD any way you want, assuming each partition is correctly aligned, and a modern OS will handle all this for you. It will not hurt anything, it will not adversely affect the access times or anything else, and don't worry about doing a ton of writes to the SSD either. They have them so you can write 50 and NBSP, GB of data a day, and it will last 10 years. Responding to Robin Hood's answer. Where leveling won't have as much free space to play with, because write operations will be spread across a smaller space, so you could, but not necessarily will wear out that part of the drive faster than you would if the whole drive was a single partition unless you will be performing equivalent wear on the additional partitions, for example, a dual boot. That is totally wrong. It is impossible to wear out a partition because you read/write to only that partition. This is not even remotely how SSDs work. An SSD works at a much lower level access than what the file system sees. An SSD works with blocks and pages. In this case, what actually happens is, even if you are writing a ton of data in a specific partition, the file system is constrained by the partition, but the SSD is not. The more writes the SSD gets, the more blocks/pages the SSD will be swapping out in order to do where leveling. It couldn't care less how the file system sees things ! And NBSB. That means, at one time, the data might reside in a specific page on the SSD, but, another time, it can and will be different. The SSD will keep track of where the data gets shuffled off to, and the file system will have no clue where on the SSD the data actually are. To make this even easier, say you write a file on partition 1. The OS tells the file system about the storage needs, and the file system allocates the sectors, and then tells the SSD it needs X amount of space. The file system sees the file at a logical block address, LBA, of 123, for example. The SSD makes a note that LBA 123 is using block/page number 500, for example. So, every time the OS needs this specific file, the SSD will have a pointer to the exact page it is using. Now, if we keep writing to the SSD, where leveling kicks in, and says block/page number 500, we can better optimize you at block/page number 2300. Now, when the OS requests that same file, and the file system asks for LBA 123 again, this time, the SSD will return block/page number 2300, and not number 500. Like hard drives, NAND flash SSDs are sequential access, so any data you write/read from the additional partitions will be farther away than it might have been if it were written in a single partition, because people usually leave free space in their partitions. This will increase access times for the data that is stored on the additional partitions. No, this is again wrong. Robin Hood is thinking things out in terms of the file system, instead of thinking like how exactly a SSD works. Again, there is no way for the file system to know how the SSD stores the data. There is no farther away here, that is only in the eyes of the file system, not the actual way a SSD stores information. It is possible for the SSD to have the data spread out in different NAND chips, and the user will not notice any increase in access times. Heck, due to the parallel nature of the NAND, it could even end up being faster than before, But we are talking nanoseconds here, blink and you missed it. Less total space increases the likelihood of writing fragmented files, and while the performance impact is small, keep in mind that it's generally considered a bad idea to defragment an AND flash SSD because it will wear down the drive. Of course, depending on what file system you are using, some result in extremely low amounts of fragmentation, because they are designed to write files as a whole whenever possible rather than dump it all over the place to create faster write speeds. Nope, sorry, again this is wrong. The file system's view of files and the SSD's view of those same files are not even remotely close. The file system might see the file as fragmented in the worst case possible, but the SSD view of the same data is almost always optimized. Thus, a defragmentation program would look at those WAs and say, this file must really be fragmented ! And NBSP. But, since it has no clue as to the internals of the SSD, it is 100% wrong. That is the reason a defrag program will not work on SSDs, and yes, a defrag program also causes unnecessary writes, as was mentioned. The article series Coding for SSDs is a good overview of what is going on if you want to be more technical about how SSDs work. For some more light reading on how FTL, Flash Translation Layer, actually works, I also suggest you read Critical Role of Firmware and Flash Translation Layers in Solid-State Drive Design and NBSP, PDF, from the Flash Memory Summit site. They also have lots of other papers available, such as Modeling Flash Translation Layers to Enhance System Lifetime and NBSP, PDF. Leveraging Host-Based Flash Translation Layer for Application Acceleration and NBSP, PDF. Another paper on how this works, Flash Memory Overview and NBSP, PDF. See the section Writing Data, Pages and NBSP, 26 to 27. If video is more your thing, see an efficient page-level FTL to optimize address translation in flash memory and related slides.
Very long answers here, when the answer is simple enough and follows directly just from the general knowledge of SSDs. One does not need more than read the Wikipedia term of solid-state drive to understand the answer, which is the advice do not partition SSD is nonsense. In the now distant past, operating systems did not support SSDs very well, and especially when partitioning did not take care to align the partitions according to the size of the erased block. This lack of alignment, when an OS logical disk sector was split between physical SSD blocks, could require the SSD to flash two physical sectors when the OS only intended to update one, thus slowing disk access and increasing wear leveling. Currently SSDs are becoming much larger, and operating systems know all about erased blocks and alignment, so that the problem no longer exists. Maybe this advice was once meant to avoid errors on partition alignment, but today these errors are all but impossible. In fact, the argument for partitioning SSDs is today exactly the same as for classical disks. To better organize and separate the data. For example, installing the operating system on a separate and smaller partition is handy for taking a backup image of it as a precaution when making large updates to the OS.
There are no drawbacks to partitioning a SSD, and you can actually extend its life by leaving some unpartitioned space. Where leveling is applied on all the blocks of device, ref. HP white paper, link below. In static wear leveling, all blocks across all available flash in the device participate in the wear leveling operations. This ensures all blocks receive the same amount of wear. Static wear leveling is most often used in desktop and notebook SSDs. From that, we can conclude partitions don't matter for wear leveling. This makes sense because from the HDD and AMP controller point of view, partitions don't really exist. There are just blocks and data. Even partition table is written on the same blocks, first block of the drive for MBR. It's the OS which then reads the table, and decides to which blocks to write data and which not. OS sees blocks using LBA to give a unique number to each block. However, the controller then maps the logical block to an actual physical block, taking our leveling scheme into consideration. The same white paper gives a good suggestion to extend life of the device. Next, over-provision your drive. You can increase the lifetime by only partitioning a portion of the device's total capacity. For example, if you have a 256 GB drive, only partition it to 240 GB. This will greatly extend the life of the drive. A 20% over-provisioning level, partitioning only 200 GB, would extend the life further. A good rule of thumb is every time you double the drive's over-provisioning, you add 1x to the drive's endurance. This also hints that even unpartitioned space is used for wear leveling, thus further proving the point above. Source: Technical White Paper, SSD Endurance. This URL.
Disk sectors have been 512 bytes for a long time, and mechanical disks have the property that the only thing that affects how long it takes to read/write a sector is the seek delay. So the main optimization step with mechanical hard drives was try to read/write blocks sequentially to minimize seeks. Flash works vastly different than mechanical hard drives. On the raw flash level, you do not have blocks, but pages and erase blocks, to borrow from Linux NTD terminology. You can write to flash a page at a time, and you can erase flash an erase block at a time. A typical page size for flash is 2 kilobytes, and a typical size for erase blocks is 128 kilobytes. But SATA SSDs present an interface that works with 512 byte sector sizes to the OS. If there is a one-to-one mapping between pages and sectors, you can see how you would run into trouble if your partition table started on an odd page, or a page in the middle of an erase block. Given that OCs prefer to fetch data from drives in 4 kilobytes chunks, since this aligns with x86 paging hardware, you can see how such a 4 kilobytes block could straddle an erase block, meaning updating it would require erasing, then rewriting 2 blocks instead of 1. Leading to lower performance. However, SSD firmware does not maintain a one-to-one mapping. It does a physical block address, PBA, to logical block address, LBA, translation. Meaning you do not ever know where, say, sector 5000 or any other given sector is really being written to in the flash. It's doing a lot of things behind the scenes by design to try always write to pre-erased erase blocks. You can't know for sure exactly what it's doing without a disassembly of the firmware, but unless the firmware is completely junk, the firmware probably steps around this. You may have heard about 4-NOTS hard drives. These are mechanical hard drives that internally use a sector size of 4 kilobytes, but still present a 512 byte sector interface to the operating systems. This is needed because the gaps between sectors need to get smaller on the platter to fit more data. That means internally it always reads and writes 4K sectors but hides it from the OS. In this case, if you do not write to sectors that fall on a 4 kilobytes boundary, you will incur a speed penalty, because each such read/write will result in 2 internal 4 kilobyte sectors being read and rewritten. But this does not apply to SSDs. Anyway, this is the only situation I can think of why it is suggested not to partition SSDs. But it doesn't apply.